Okay, we continue our discussion. We were talking about payload, and we discussed about the transparent payload, which is another term people use, which is called bent pipe in the sky. So, it is bent pipe transponders or bent pipe payload. But then there are certain requirements through for that people use much more complex transponders, which is called onboard repeaters or onboard switching repeaters. Onboard switching repeaters, let us say for multi-beam operation, different spot beams are used. We will discuss about that later. There may be requirement from sending the subband signal from one beam to the another beam. This is done by the microwave switching matrix on board or IF switching matrix, converting to intermediate frequency and matrix. It can be regenerative also. The signal can be demodulated and regenerated. So, it is called regenerative transponder. So, that is another form when there is a requirement for the baseband data has to be extracted and then routing is done through the switching. So, after demodulation switching is done and remodulation is done after the IF stage. So, this is much more complex. In that case, advantage is uplink noise is not directly amplified, because you have come down to the baseband and then going up from the baseband. So, the noise is not transferred to the downlink. That is one of the advantage. So, in the symmetrical or balanced link, when uplink and downlink are symmetrical link, we will discuss about that later. Regenerative transponder has certain 3 dB advantage over the bent pipe transponder. We will discuss that one much later. A very short block diagram, we will not discuss in detail of that, but short block diagram is this is the receiver, very small symbol put this block as an amplifier and the mixer, means is down conversion together. So, from different beams it is coming and then they are put into a demodulation. I said a demod, actually there are many demods here, and then after that there is the processing or routing or switching is done at the digital level, baseband level, and then it goes into the modulation and then up conversion and then amplification. So, this part after the receiver is called regenerative transponder, which includes the bent pipe transponder, that is the OMUX, DMUX and the amplifier, also the demodulation, remodulation along with the switch, which is regeneration, both together. It is called regenerative transponder. Now, with this we go into one of the another important subsystem which is there on board as well as which comes on the ground is antenna. We will discuss the antenna briefly now, and more details of the antenna we will discuss later as we go through this course. The antenna is an important thing, that is we are trying to take a certain advantage from the antenna, in particularly in satellite communication. Antenna is required for wireless communication. It is nothing but it is a reciprocal device. The same antenna can be used for transmission as well as for reception. Now, I will try to plot antenna is directive. So, you can think of a coordinate system which is theta phi r coordinate, r theta phi coordinate system. So, a received signal level is as a function of the angle theta is known as radiation pattern or transmit signal level. As I said, it is a reciprocal device. So, transmit or receive signal level material. In a linear scale, it can be plotted like that in x direction if it is the theta angle or phi angle. Here I have shown theta, and then the power is at 0 degrees maximum power, let us assume, and then as we increase the theta either in positive direction or negative direction, the power falls and it peaks again, it falls again, peaks again, like that. So, the main peak is called the main lobe and the small peaks are called side lobes, and from the maximum power, when the power falls at a particular angle of theta, when the power is half of that maximum power, it is minus 3 dB point. So, this angle is called theta 3 dB. As engineering approximation, we will try to always use this theta 3 dB, which is half power from the maximum, and this maximum power direction is called bore side. The maximum power direction of the radiation pattern is called bore side. This radiation pattern can be drawn in theta phi coordinate also. is a linear way is done. And half power beam width is the angular separation between half power across the bore side. Now, let us try to see how much we are focusing. So, that can be expressed by a term radiation intensity, that is nothing but a power radiated per unit solid angle in theta phi direction, let us call P theta phi from an antenna in theta phi direction per unit solid angle. So, therefore, we can define a term called directive gain capital D, which is also theta phi direction. Directive gain is the measure of the focusing property of this antenna, which is P theta phi and transmit power by 4 pi. This Pt by transmit power by 4 pi is the total radiated power per unit solid angle. So, the ratio of P theta phi by Pt by 4 pi, that is the directive gain, but this is with the radiated power. We have certain power amplifier output which is going to the antenna, which is the input power to the antenna. So, therefore, this has to be translated into the input power. Now, the power which is going to the satellite antenna as the input may not be fully radiated, because there may be some loss in the antenna system. So, there is certain efficiency. So, that transmitted power is some factor of the input power, which is we call efficiency, that is eta. Eta in this case is the efficiency of the antenna. So, input power is a power input to the antenna, and then we can define another term antenna gain G in again theta phi direction is the ratio of P theta phi by P input by 4 pi, and P input by 4 pi is Pt by eta 4 pi. So, this whole ratio is P theta phi divided by Pt by eta 4 pi. Now, this eta can be taken up. So, it is P theta phi by Pt by 4 pi, which is nothing but directive gain d theta phi. So, G, which is we call antenna gain in theta phi direction, is the efficiency time eta times the directive gain d theta phi. So, this efficiency determines the how much power which is going as the input to the antenna is really getting radiated. So, efficiency should be as high as possible. It depends on the antenna design. Now, this G again is related to some physical parameters. Generally, this antenna gain G is referred to the bore side. We will not go for G theta phi detail. So, G is generally taken as bore side, the maximum gain. So, it is actually G max. So, G is 4 pi of effective aperture of the antenna by lambda square. This effective aperture is eta times the physical aperture, because there are certain losses in the aperture. Aperture may not have exactly the way it is supposed to transmit. So, 4 pi eta a by lambda square, and a as we know is pi d square by 4. So, the G is expressed in terms of eta into 4 into pi d by lambda whole square. This 4 gets cancelled, pi d by lambda whole square. Now, this also can be related to the theta 3 dB, which is nothing but beam width. The half power beam width theta 3 dB is expressed in terms of wavelength and antenna diameter. It depends on the radiation to the antenna, and generally in case of satellite antenna we use because higher focusing ability is required, we use a parabolic reflector. So, as I gave you last time example ATM near bank ATMs, you will find certain VSATs, the reflector is parabolic. You might have seen that there are direct to home services through which you receive the TV, that is on the rooftop, many people have put, that is also a reflector, parabolic reflector. And the cable operators, they also use parabolic reflector. For satellites, normally on satellite also there are parabolic reflector. The picture of the satellite is what I shown you earlier. So, the diameter of that parabola, the face of the parabola is called is here small d, and the the wavelength on which is operating is lambda, and depending on the radiation pattern of the primary feed to the reflector, this term, this number 75 is appearing. So, theta 3 dB is 75 lambda by d. This 75 is just a typical number. Some of the books say it is 72, some people take 70. It is just an approximate number. So, here we have taken 75. Theta 3 dB is 75 lambda by d. Other way we can say d by lambda is 75 by 3 dB. Why we say d by lambda? Because previous expression we have seen gain in terms of d by lambda. So, the gain then can be expressed as eta times pi square 75 square by theta 3 dB square, because d by lambda is replaced there, 75 by theta 3 dB. And if you take efficiency eta 60%, which is generally true, if you put these numbers there, approximately this number comes as a 33,310. Some people take it as 33,000, some people take it as 33,300. You can go to very near 33,309 point something. Okay. So, these are all thumb rules for calculation. So, gain is related to a number by theta 3 dB square. So, theta 3 dB and gain can be found out the other one if it is known. Let us see, for a quick calculation, a global beam at the satellite at GSO subtends 17 degree angle. You just recollect in our orbit discussion, the 17.4 or some other angle we have calculated, almost 17 degree angle global beam. Assuming theta, that is the theta 3 dB of the satellite. So, what should be the satellite antenna gain and its diameter at 4 gigahertz, because lambda is coming at 4 gigahertz, what should be its diameter and the gain? Easy calculation. D by lambda first you calculate, that is 75 by theta 3 dB is 75 by theta 3 dB is 17 degree. So, it is d by lambda ratio is 4.4. So, at 4 gigahertz lambda is roughly, let us take 0.075 meter. So, d is 4.4 multiplied by 0.075 comes to 0.33 meter or 33 centimeter, A4 size paper, and corresponding gain, assuming that thumb rule 33,310 by 17 square theta 3 dB square is equal to, in terms of dBi, when you calculate, it is 20.6 dB. I have put dBi, dB with respect to isotropic antenna. When we discuss about the antenna detail, we will come across all this. Right now, you take this as simple dB. So, gain max will be 20.6 dB and the diameter of the antenna is less than meter. So, for that is for global beam for 17 degree angle. Now, let us see what will happen for smaller angle, which is 5 degree, which covers roughly from geostationary satellite roughly India and landmass. To cover India and surrounding ocean neighboring countries, what will be the satellite antenna diameter and gain? You just, instead of 17 you put 5. So, you get d by lambda is 75 by 5 is 15, at 4 gigahertz lambda is 0.075, d is 1.125 meter. So, 0.33 meter to it has become 1.125 meter, and gain is increased to 31.24 dB. So, that is just roughly to show you some thumb rules of the antenna calculation. So, satellite antenna can be global, regional, or much smaller, which is spot beams on the service requirement. It can be shaped, it need not be always circular or elliptical on the ground, it may be shaped in different shape, so that wastage the radiation non-service area like sea and other places can be avoided. And shaping the beam can be done by reflector shaping, and various techniques are here, array antenna, various techniques are there. Now, one of the important part of the antenna is polarization. Polarization is orientation of the electric vector field of the propagating electromagnetic wave. The polarization diversity sometimes used in the satellite communication. We have seen for isolation, I said orthogonal polarization has to be used, polarization diversity. You have to reduce the interference for to impure polarization if it is to be considered. Now, that can be expressed in terms of cross pole interference, the term is XPI, and cross pole discrimination XPD. Polarization could be linear if the electric field is linear, it's vertical or horizontal with respect to the antenna from where it is being transmitted, and it could be circular also. in the right hand circular side or left hand circular side, LHC or HC, and this axial ratio is the ratio of electric vector maximum to the electric vector minimum, and for circle it is same, for ellipse it may be different. So, it can be 3 dB. To understand what is XPD, let us see there is a electric field which is transmitted, A vector is vertical and horizontal vector B is transmitted. Now, at the receiver, because of some impurity, this vector may have a component of Ax in the x component falling and copolar component, that is the vertical. So, if there is a x component coming, that is cross pole component coming over the copole, the cross pole discrimination is defined as 20 log A copole by A cross pole, AC by Ax is 20 log in dB, and cross pole interference is 20 log AC by Bx, when the B is transmitting, its component, cross pole component is Bx. So, AC by, so actually cross poles XPI gives us how much interference is occurring. So, for orthogonal polarization with good pure antenna design in the transmit and receive side, this should be XPI should be as high as possible, that means Bx should be as low as possible, ideally it should be 0. This advantage is certain, sometimes it is taken. Some questions I am putting, you try to find out your answer. What is the effective aperture of a isotropic antenna operating at a wavelength of 1 centimeter? You try to use the formula. An LHCP satellite transmit antenna has 3 dB axial ratio. For a linearly polarized mobile antenna, that means the transmit antenna is a LHCP and receive antenna is linearly polarized antenna, that is circular polarized transmission and linear polarized reception. So, what is the maximum variation expected in the receive power? No variation, 2 times variation, 3 times variation, find out the answer. Okay. So, with this we close the antenna chapter. Let us go into the environment on which the satellites are operating. Satellite environment, a couple of things occur there. It is gravity is very low, 0 gravity. So, there are difficulty in the liquid flow, whatever fluid is there, there will be certain difficulty. So, but there is certain ease of antenna deployment, because there is no additional force acting on it or solar panel maneuvering. There is no atmospheric pressure, which are negligible atmospheric pressure of the order of 10 to the power minus 7 torr. So, that increases the friction between the moving surfaces, and special lubrication is needed for that. Outgassing of electronic components increases the surrounding gas pressure. Outgassing means because the vacuum is there, so some gas forms comes out of the electronic component, that will increase the gas pressure. So, negligible atmospheric pressure may be reduced a little or increase the atmospheric pressure, or local pressure, environmental pressure is increased. There is a high temperature variation we have seen in thermal design, that dynamic range is quite large. Space debris and particles that might be occurring on the satellite body, proton, electron, cosmic rays, meteorites, man-made objects, reduction in solar cell efficiency is possible. Finite eccentricity of the Earth's surface, Earth orbit, there is a variation of solar flux resulting the variation of solar power generation, these we have seen already. There is a magnetic field, Earth magnetic field is very small, there is almost 1/300th relative on the Earth's surface. So, that does not have much effect. There is a Van Allen belt, which is the cosmic particles, charged particles move around the Earth, and they are forming a dense layer. So, that can create problem in the electronic devices which are passing through this belt. This belt is almost from the surface of the Earth around 20,000 kilometer above the surface of the Earth. So, the satellites which are passing through this belt has to be protected properly. So, the life of the satellite mainly depends on the onboard fuel capacity and the failure of the component sensor system, which depends on the reliability. Lifetime is presently kept as 15 years. The onboard fuel capacity part we have already discussed, that when the fuel is much less, then it is deorbited. So, how much fuel is left, that depends on. roughly it is 15 years to, some satellites are also 20 years satellites, some satellites are 7 years to 10 years satellite. But let us concentrate more on this subsystem reliability or component reliability. Reliability of the satellite is mainly governed by the reliability of the critical component. The reliability can be improved by keeping the redundant components ready at the satellite, so that you can switch it. Redundant components are replaced the failed component through the switches, so the path is changed. And however, it is not always possible to keep the redundancy for all the subsystems like antenna, like solar panel. These cannot be having redundant, too much of weight you will be carrying unnecessarily. So, we will try to see how we do the reliability engineering. Reliability by definition is the probability to perform intended function over specified time and operating condition. Probability to perform over the specified time and over the operating condition. So, reliability is defined in as the exponential of the component failure rate into time over the time, that is minus integration of 0 to t lambda dt, and lambda is number of components failure in given time by number of components that is surviving, that is the failure rate. Generally for all components, whether it is space or ground, it follows a lifetime cycle where initially it fails, failure probability is quite high. During the lifetime longer period, the probability is random failure, and then there is a time comes when it is wears out. It is true for the human life and life on earth, everything it is true like this. The most components follow this failure pattern. So, we will try to operate them in this region where it is random failure. In satellite system, careful selection of the components are done based on the component's complexity, its heritage, where and how it is used, how it performed, its manufacturing process, its manufacturer's certification, that is its credential, spent life in the shelf, and then in the satellite system the initial part of the failure of the component is tested, and intentionally those who are supposed to fail, let them fail by a test called burn in. That means you keep it on for 168 hours or roughly about 7 days with a specified input, output load, power, temperature, pressure, relative humidity, etc. With all the specified condition, you continuously keep it on for 7 days. So, if it is supposed to fail in the infant condition, it will fail there. Which component subsystem pass this, they are taken for the satellite fabrication. But the main aim is to eliminate the random failure during this operating lifetime. So, that is done by reliability engineering technique. The wear out phase can be delayed by improving the material selection and the manufacturing process. Okay. So, let us try to calculate what is the what should be the improvement in the reliability engineering, how can we do it. So, we have seen this r is equal to exponential to the power minus integration of 0 to t lambda dt, assuming constant failure rate over time. So, it can be e to the power minus lambda t, which is e to the power minus t by m, lambda is 1 by m, which is mtbf, or m is equal to 1 by lambda, which is mtbf, mean time between failure. Mtbf is mean time between failure. When the components are connected in series, failures of the component, any failure of any one of the component fails the complete system. So, the total reliability is overall reliability R0 can be multiplication of R1, R2, R3 up to Rn, and these R values vary from 0 to 1, is fraction. Let us see the numbers. What is the reliability of two components in series when R1 and R2 both are 0.9 and when R1 is 0.9 and R2 is 0.7. Multiply them, overall reliability when they are both are 0.9 is 0.81. So, it is less than the individual reliability. When it is 0.9 and 0.7, it is 0.61, it is lower than the lowest one. So, overall reliability is lower than the lowest, but when they are connected in parallel, then the components, when all the components fail, then only there is a failure. So, therefore, we can say the system failure occurs when all the components are unreliable. Okay. That can be calculated. Consider a system with I number of parallel elements in which reliability of each component is independent to all others. If Qi instead of r, let us term Qi is unreliability of the ith component, then the probability of all units will fail is the product of Q's, that is overall unreliability Q0 Qo is Q1, Q2, Q3 up to Qi, or when all of them are equal, the overall reliability Qo is Q to the power I, and unreliability has decreased because Q to the power I, Q is, since r is less than 1, Q is also less than 1, Q to the power I is less than Q. Therefore, the reliability is R overall is Ro is equal to 1 minus Qo. Overall reliability can be derived from individual elements of reliability like this, that is Qo is multiplication of Q1 to Qi, and when all of them are equal, Qo is equal to Q to the power I, R is 1 minus Q. So, Ro is 1 minus Qo. So, 1 minus Q to the power I is 1 minus R to the power I. This way you can calculate. If the reliability of individual numbers are known, overall reliability when they are parallelly connected can be found out from Ro is equal to 1 minus R to the power I. What is the overall reliability of two components that connected in parallel when both are 0.9? By putting the same relation, Ro is equal to 0.99, because it is 1 minus R1 into 1 minus R2, which is 1 minus 0.9 whole square is 0.99. When R1, R2, R3, three components are connected in parallel and all of them are 0.9, you can see overall reliability is increasing 0.999. When two of them it was 0.99. So, by increasing the number of components connected in parallel, you can increase the reliability number. Parallel configuration improves the overall reliability. In practice, redundant components are kept in parallel through the switches. Primary component fails, redundant component is used, thus improving the overall reliability, but this changeover is done by switch and command. The switch reliability and this command reliability is also very important. In case of satellites, all this subsystem, payload, all have certain failure rates, and all the reliability estimation is done as if they are connected in series. So, overall reliability of the satellite is as if AOC, STTC, propulsion, thermal, etc. payload, everything is connected in series, though physically they are not connected in series. It is reliability purpose. So, overall reliability is reliability of individual multiplied overall reliability of the satellite. So, payload, when one receive subsystem, transponder system and antenna system is used, then it is multiplication of individual reliability. Payload, R payload is R receive, R transponder, R antenna. When transponder is connected in parallel and receive an antenna, receiver and transmit receive antennas are in series, then it becomes overall payload reliability R receive antenna, R receive multiplied by 1 minus R transponder square, because two of them are there, into R transmit antenna. This redundancy increases the mass. So, therefore, figure of merit is R by M. M is the increase in mass due to redundancy, and R is the ratio of reliability with redundancy and without redundancy. There is also increase in the mass and cost due to redundancy due to addition of switches and the failure of sensors. So, what we covered till now is satellite bus, payload, antenna, environment and reliability. Very briefly, we have covered the space segment. We stop here now. Thank you very much.